Hello and welcome to a special edition of our class notes. Make sure you get this into your notebook. We are going into a new unit, and that is on triangles, and we're going to be talking about angular and right triangles. For the most part, we're going to focus in on right triangles for now, and then we're going to talk about some non-right triangles using some very special equations, or which is law of sines and law of cosines. But before that, we need to talk about right triangles, and we're breaking this up. So right triangles, we definitely need to start off with what a right triangle is. It's a triangle that has a right angle in it. And let's go ahead and draw one. And very often, a right triangle is associated with the Pythagorean theorem. So I'm going to draw a right angle here, and we always have a right angle where the two legs are A and B, and typically, and then the hypotenuse is always C. That is always the most important side to identify is the hypotenuse. That is always the longest side of any right triangle, and then A and B are known as the legs. So we could call this leg 1, we could call this leg 2. Okay? And as we know the Pythagorean theorem, hopefully we recall, the Pythagorean theorem is used only, that looks terrible. It looks like there's no E in there. Theorem is only used for right triangles, where a squared plus b squared is equal to c squared, where c is the hypotenuse. So that is an important feature, that this is always the hypotenuse. So quick recall, you could use this for whenever you have two sides of a right triangle, okay? So that is when you would use this. So used when given two sides of a right triangle. All right, so for instance, if we have a triangle, let's do some quick examples. If we have, for instance, here's your examples. First one, if we have a triangle that has length 3 and 4, and we definitely have a right angle here, then we could solve for the last side, or the C side, or the hypotenuse. So all we have to do is we could label this A or B. It doesn't quite matter because they're the legs. Legs don't quite matter. You also might see this, just a heads up, you might see this called leg 1 squared plus leg 2 squared is equal to hypotenuse squared. That's another version of the Pythagorean theorem, just as a small heads up. So back to this example. A and B are the legs, so we do 3 squared plus 4 squared is equal to c squared. 3 squared is 9, 4 squared is 16, and we get c squared is just c squared. Add these two up to get 25 is equal to c squared. Square root both sides, and typically whenever you square root some value, you get two answers, a positive and a negative. But since we are working with something that has length, normally we would have a -5 and a +5 is equal to c. But can you ever have negative lengths? Absolutely not. So we say c is only equal to 5, or 5 units. So depending on what the units are, we would just, if there's no units actually measured, then we say units. Okay? Now, what if we have another example? For instance, B. We have another, let's do this. Let's draw another triangle. And we'll do, for instance, let's say this was 2, and this had a length of 10. Here's your right angle, and we could go through this. Okay, what is this last side? Well, we know for sure that 10 is the hypotenuse, so that's always the most important side to identify. We could call this leg 1, we could call this leg 2, as opposed to A and B, however you want to do it, and we could do the work this way. So in this particular case, it's going to be A squared plus B squared is equal to C squared, or leg 1 squared, 2 squared, leg 2 squared, I'm going to call that B, is equal to C squared, 10 squared. 2 squared is 4, plus B squared is equal to 10 squared is 100. Now we would solve this as a normal algebra problem. We have b squared is equal to 96. Square root both sides, and this is where we're going to need to do some work. Technically, yes, we would have to get a plus and minus version of this, but we don't deal with negative answers, so we could work with only the positive version of this, and we could break this down. Now, if you know your perfect squares, awesome, because then you could do 1, 4, 9, 16, 25, etc., etc. And if you know your perfect squares and you know your factors of 96, then you might be able to know that, hey, 16 goes perfectly into 96. So you say this is square root of 16 times the square root of 6, because they multiply to 96. And then since 16 is a perfect square, we could then say this is 4 root 6. Square root of 6 doesn't simplify any further, so b is equal to 4 root 6. Simplify your radical as much as you can whenever you can. So there's your Pythagorean theorem review. Okay. Just as a small note, we also have, if you remember this, and I didn't mention this earlier, but if you remember this, we also have triples, Pythagorean triples. So this is worth mentioning just because it makes it easy to remember some of your more common Pythagorean kind of, I guess, triangles that have integers as whole values. So 3, 4, 5 is a very common one, because, and then you could always multiply by 2. So for instance, you can multiply everything by 2, you get 6, 8, and 10. So you can multiply by 3, and you get 9, 12, 15, and it goes on and on and on. Another common one is 5, 12, 13. Notice that I'm putting the hypotenuse last on purpose. 7, 24, 25 is another common one. 8, 15, 17. And then the last common one that I'm going to talk about, obviously 6, 8, and 10 is a 1, but 9, 40, and 41. So I'm going to leave it at that. These are just good to kind of have handy in case we do recognize some Pythagorean triples in right triangles. So Pythagorean triples. Okay. Now we should also be able to identify some trig ratios. So part 2 to this lesson is trig ratios. I'm going to put a little divider here. I'm going to do trig ratios. And this is where our trigonometry actually kicks in, our SOHCAHTOA. Now, we've been working a lot with this all year already, so this is not anything new. SOHCAHTOA, except now we're dating it back to right triangles specifically. SOHCAHTOA, or all spelled out. SOHCAHTOA. I personally like, I'm so used to writing it this way. I personally like the top one because it actually shows you the ratio of what they are. Now, sine of theta is always going to be equal to the opposite side over the hypotenuse. I'm going to shorthand this because hopefully you've seen this before. Cosine of theta, remember theta is just an angle, is always equal to the adjacent side, ADJ, over the hypotenuse. And last but not least, tangent of theta is always equal to the opposite over the adjacent. Okay? And when you're given a triangle, I'm going to have to probably just do this. And if I do a quick example, write the trig ratios. Let's just do it on the one below, next page. So example, write the trig ratios for the following. Okay, and I'm going to draw a triangle. I'm going to call this right angle here. We're going to put C here. I'm going to put capital A and capital B. Okay, so here, this first one, I'm going to put sine of A. I'm also going to put in some measures here. I'm going to put a 12, a 5, and a 13. Notice that this is a Pythagorean triple, 5, 12, 13. 13 is the hypotenuse, so it should belong on that particular side. And we are looking at it from this particular perspective. So what is the trig ratio? Ratio is a fraction, or a comparison of two values, of sine of A. Well, you should put a person here for the perspective. we are looking at it from this perspective. So that means 5 is the opposite side, 12 is the adjacent side, and then 13 is the hypotenuse. Okay? And then we could say sine of A is equal to opposite over hypotenuse, which is 5 over 13, and here's your ratio. Okay? Now we could continue this. We could go down the list. Cosine of A is equal to adjacent over hypotenuse, which is 12, the adjacent side 12 over the hypotenuse 13. We'll go a step further. Tangent of A is equal to the opposite over the adjacent side, which is 5 over 12. Now what happens if I said, write the Trig ratio for sine of B? So sine of B is a different person. I'm going to put this person in a dress just to change it up. This is their perspective. So this changes and says that now the 12 is the opposite side. Okay? And then adjacent means next to. So, oops. Let's get rid of that. Now 5 is the adjacent side. And then this is 13 is still the hypotenuse. So from that perspective, the sine is actually a different ratio. It is now 12 over 13. Okay? Cosine of B is going to be equal to 5 over 13. And last but not least, tangent of B is going to be equal to opposite over adjacent. So we're looking at the blues, 12 over 5. So there's your trig ratios. Okay? We could do this a lot, but what's important to know is that your perspective from what particular angle is really, really important. And this is really important in terms of solving trig. So when it comes to actually solving trig, and do another dividing part, we could then say, okay, trigonometry for solving for sides. So in this particular case, we will use SOHCAHTOA. So I'm not going to rewrite that, but you need the trig ratios to actually solve it. So given, this is always going to be given one side and one angle in a right triangle. Okay, so first one, if I give you a right triangle and we only have one side, let's call this 30 degrees. I call the opposite side x and the hypotenuse 10. We could then, okay, solve for x. We could say, okay, let's put our person here because that's where our angle is. And we could say, okay, x is the opposite side, 10 is the hypotenuse, which I should have labeled first because it's the most important side to identify. And we could now say, okay, we're working with opposite and hypotenuse, so that means we need to work with sine. Sine of theta, but this time around, theta is 30 degrees. So we're going to work with 30 degrees is equal to opposite x over hypotenuse 10. And this just becomes a trig problem. Okay? Sine of 30 can be calculated by just throwing that into your calculator, or personally what I would do is I would just start isolating the x. Once you do this, multiply both sides by 10, then you could actually multiply this side by 10 as well. Anything you do to one side, you do to the other. You get x on one side isolated, and you could start using your calculator. Make sure your calculator is in degrees. Okay? So this is important. Sorry, not that. Calculator in degrees. So that's your mode. Okay, you need to make sure that this is the case, because if you do not do this, then you will get these wrong. Okay? And then all you do is type in 10 times the sine of 30. And I'm doing this on a separate calculator. So times sine of 30. And I'm currently in the wrong mode. So let's make sure we are in the right mode. Degrees. And we get 5. Okay, and here we have it. X is then equal to 5. All right, so let's try another one. Let's do, here we are. My next example. All right, next example, B. Let's draw another triangle. Let's make this a right angle for, ooh, I forgot to put this right angle here. That's bad on me. So where this is most useful is when we don't have, for instance, a 30-degree angle, because we could actually use special right triangles to do that. Here, we're not gonna have one. Here, I'm gonna say this is 25 degrees. So we can't use special right triangles to actually solve this. If you remember special right triangles, awesome, because then you would know opposite of the sine is always 1/2. But anyway, this one, let's say this is y, and this is 8. And let's put our person right here. Solve for y. Well, first side I see, hypotenuse. We have 8 for the adjacent, so that means we need to work with cosine. Okay? Cosine is then equal to, cosine theta. We know we're working with 25 degrees from this perspective, so cosine of 25 degrees is equal to adjacent side 8 over the hypotenuse y. Well, this one's a little different because now we actually need to solve for y. Since y is in a denominator, we need to multiply that out first. Multiply both sides by y, y's cancel out, and we get y times cosine 25 is equal to 8. We need to isolate the y still, so we divide by cosine 25, divide by cosine 25, and this is the point where I would plug this into your calculator. Whatever this is, plug into your calculator, 8 divided by cosine 25. Close the parentheses at the tail end of this, just in case. And you should get y is actually approximately, because this is going to be a decimal, 8.83. Hopefully you got that. If you did not, make sure you're in the right mode, and we could keep going. Last one, C. Another triangle. Actually, let's change this around. Let's do this upside down. Okay, right angle. Let's put an 8 here. Let's put a Z here. And let's put a 55 here. So this time around, I'm going to put my person right here in green. Recognizing opposite of this 55, this is our perspective, is the 8. Adjacent is the Z. Trig function that works with opposite and adjacent is tangent. So we do tangent of 55 because that's our angle perspective, is equal to the opposite side 8 over the adjacent side Z. So just like the last problem, we're going to have to multiply both sides by Z to start isolating it. Z's cancel out, and we get Z times the tangent of 55 is equal to 8. Divide both sides by tangent of 55, and the tangent 55's cancel. We get Z is equal to, this should be approximately 5.60. Now, I would definitely say go to the hundredths place just to make sure we are keeping it as accurate as possible, especially when it comes to multi-step problems. But that is our quick rundown of our right triangle trig, pretty much a review lesson from geometry. There's 3 major lessons we need to remember: Pythagorean theorem and their triples as a bonus, trig ratios, how to write them, and then solving for sides, okay, using sine, cosine, and tangent to solve. If you do have any questions, please let me know, and the next time we will be solving with inverses and solving for angles. If you have any questions, please let me know, and I will see you next time. Bye.